Okay, thank you, Francesca. Yes, I will continue to talk about large uncertainties and asymmetric intervals. And I will basically present a recent publication that we made. So I consider this topic still to be at the research stage. And therefore, I use the word here, suggested expression for asymmetric measurement uncertainty intervals, just to emphasize this. Yes, I will just do this by giving some background here, and I will give a background just by making a couple of statements here. So uncertainty intervals are typically reported as symmetric intervals, and these symmetric intervals, as we've heard in the previous talk here, cannot really be used for high expanded uncertainties. So in a case, for instance, when we have an expanded uncertainty of 100%, it's very unreasonable to have a symmetric interval. And this is something that is not covered well, I think, in common measurement uncertainty guidelines. It is covered in the Eurachem sampling uncertainty guidelines, but else in other type of documents, I think this is a missing topic. And I will also say that in many instrumental techniques, results are often generated by a multiplicative combination of random variables. And then the distribution of measurement results will be driven towards a log normal distribution, which is an asymmetric distribution. But at small or modest relative standard uncertainties, and then we're talking below 15 to 20%, the normal and a log normal distribution are so similar that the normal distribution will serve as a very suitable approximation here. But at large relative standard uncertainties, again, above 15 to 20%, we need to consider asymmetry. And a common way of doing this is, as Bertil talked about here before, is by transforming data using a logarithmic transformation. And then the uncertainty interval can be calculated in this way. And we can also use the uncertainty factor and express it in this way. So it's typically assumed that distribution of measurement results can be approximated with either a normal distribution or a log normal distribution. But what we have suggested recently is to use another type of transformation that is written here. So here we use a power transformation instead. And the parameter B here is a parameter that needs to be optimized with the goal that transform data should have a skewness close to 0, which means that they will become symmetric. And then we can write this expression like this instead. And I should also say that this transformation here, it's widely used in statistics, but what I'm aware of, not in measurement uncertainties so far. But it's widely used in statistics, so it's a well-established way of transforming data. And I will explain a little more about how this transformation works here. So we have what I call a B scale here. So here you will have B values that will transform different distributions to symmetric distributions. And there will be two reference points here, which I've marked here, 0 and 1. So with a B value of 1, we will not perform a transformation at all. And if we start with normal distributed data, this will then, of course, remain normal. If we instead have log normal distributed measurement data, then an optimized or a proper value B will be close to 0. We can't really use 0 because then all data will be transformed to 1. But we could use B value that will approach 0 for this. And if we then have distributions that are what I consider or call between a normal and a log normal distribution, a proper value of B will then be somewhere between 0 and 1 here. So basically here you will transform asymmetric distributions with a positive skewness. If we have distribution with a negative skewness, not very common, but it could actually happen in some methods, then a proper B value will be above 1. So here you will transform distribution with a negative skewness to normal distributed data. There could also be some distribution where you will find a proper value of B being less than 0. That is, you will have negative B values. I will not go into this here in this short presentation. It's a little more difficult to explain and understand this part. So I will just leave that for now. Now, we're going to find a B value here. And this can be used using mathematical tools available in many calculation softwares. However, in reality, it's difficult to find a B value. And at least based on experimental data, you need large numbers of data, typically above, I would say, 10,000 ideally. And such amount of data are rarely available. But the best you could do is to look at control samples and control charts. And these typically describe what I call within laboratory reproducibility. They can contain data typically in the order of 100 to 2,000. So, if we start without any information of a proper value of B, there is a few things that we suggest to do. When coefficient of variation is less than, say, 15%, it's quite reasonable to assume optimized B value less than 1, equal to 1, which means that no transformation of the data is performed at all. And for these low coefficient of variations, a B value is actually not critical. And this basically reflects that a normal distribution and a log normal distribution are so similar at these low CV values. When CV is above approximately 15 to 20%, it's often sensible to assume a B value close to 0. We can't use 0, but we could use, for instance, 0.0001 or something like that. And this is basically the same as assuming a log normal distribution. We could also sometimes use Monte Carlo simulations. If we have a relevant model equation, it could be possible to generate large amount of data and then use that to find a proper value of B. And alternatively, there could be some cases maybe where you can have a general agreed value of the of B that might be used also. So now we're going to construct an uncertain interval. And a symmetry is basically for the symmetry in an uncertain interval will actually come from two sources here. We will have a symmetry in the distribution of the measurement results, and that is handled by this expression, as we have seen. But there will also be asymmetry coming from the fact that the standard uncertainty will increase proportional to the measurand. And this is handled with this expression here. And here you basically assume a normal distribution of results and that the relative uncertainty is independent of the concentration, which we have seen is quite reasonable for many methods in large concentration ranges. And what we do here with this expression here is that we actually take into account that the absolute uncertainty will vary with concentration in the uncertainty interval. So this expression here will basically take care of or be valid for when you have a normal distribution and when the relative uncertainty is independent of the concentration. And then we will combine these two expressions here, and we will end up with this at the bottom here. And we will look a little more on this expression here. Where if we have normal distributed data, a proper value B will then be 1. And then this expression will transfer to what we have in the right corner here. So again, this is an expression taking into account that when the relative uncertainty is independent of the concentration, the absolute uncertainty will depend on the concentration. And this is taken into account with this expression here. If we instead have log normal distributed measurement results, this expression will give exactly the same interval as calculated using this expression here. And this is not obvious when just looking at them, but if you try this, you will find that you will get exactly the same intervals with these two expressions. And then, of course, if we have other types of distributions that are somewhere between what I call a log normal and a normal distribution, we can handle that with a proper value B. There is a general issue with measurement results having an asymmetric distribution, and I will just point to that here. When you use transformation based on either logarithmic transformation or a power transformation, as we have suggested here, this will result in symmetry around the median. And the uncertainty interval in the original space will then cover the median with a given probability. It's typically 95%. So then the question is the median equal to what's intended to be measured? And yeah, this is a difficult question, and I will just raise that question here without answering it. Now, we will look at an example here. This is real data we have calculated on. It's for determination of sulfur in gas samples using gas chromatography with chemiluminescence detection. And here we actually have a control sample that have a lot of measurements done on it. We have 740 measurements. The relative standard deviation or coefficient of variation here is 15%. So it's actually when you need to start consider asymmetry. That's why we have chosen this example here. When we optimize B to transfer this, the distribution of the control sample, we will find that a b value of 0.4 will transfer these results to a normal distribution. So here we actually have a distribution for the control sample that is somewhere between a normal and a log normal distribution. And then we have calculated uncertainty intervals in different ways and compared them. And the upper part here, the upper interval, we have calculated an uncertainty interval around a nominal value of 10 based on the power transformation that we described here. And we will end up with this interval here. We have also used transformation based on a logarithmic transformation. And then we will get uncertainty interval looking like this, bottom. And we have also calculated uncertainty interval in a more traditional way. So we have done this without transformation, which means that we assume a normal distribution of the measurement results. And first we have neglected that the standard uncertainty will be different in the upper and lower limit of the uncertainty interval. So here we'll get a symmetric interval. And then we have also done this by taking into account that the standard uncertainty will be different at the upper and lower limit. And then we will end up in this uncertainty interval here. So this is a comparison of different ways of calculating uncertainty intervals when the coefficient of variation is around 15 to 20%, which is when it starts to become necessary to consider asymmetry. So this will basically show the difference between different uncertainty intervals at 15 to 20% here. If we have larger coefficient of variation, all these differences will be more pronounced and it will be more critical to take asymmetry into consideration here. There is a recent publication about this. It's in Accreditation and Quality Assurance, and you will basically find the reference here. So if you're interested in this, here is the reference for this. So basically, this is something we have published recently. I consider this still to be at the research stage, and we will continue to look in this and evaluate this way of handling asymmetry in the future here. Yes, that was the end. Thank you very much for listening to this, and I guess it's up to Francesca to decide if there is room for any questions here.